said, hey, you, let's do some diffy Q. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some diffy Q. In this video, we'll look at singular points. Just like when we talked about Taylor series, we center a Taylor series around a given point. So too do we do this with series solutions to differential equations. We center them around a given point. The points that we can center the series around determine how we should set up our series. Some points we should set them up differently than others. In particular, we want to look at whether those points are ordinary or singular points. We say an ordinary point is a point x naught such that if you look at the first coefficient function, a sub n of x, and substitute in this point, if what you get is something besides 0, that is, if this value evaluated at x naught is not equal to 0, then we call that an ordinary point. One way to maybe remember that or think of it as ordinary is it doesn't really change the order of this differential equation. Likewise, we have a singular point if it is equal to 0. And the notion being there is it cuts the order of the differential equation. Plugging in various points for x, we may get that some of the terms disappear because their coefficient evaluated at that point is 0. But there's something noteworthy about when the first coefficient or the highest order coefficient and highest order term disappears, because that changes the order. Even if some of these latter terms disappear, the order would be the same as long as it had a non-zero coefficient. But as soon as this disappears, now the order of the differential equation is changed. And that's in particular the most notable thing that can happen as you plug in different x values. Now let's look at examples where we find singular points. Here we have three different differential equations. In the first case, we have a first order differential equation. Now we look at the highest order term and we see what x values or what independent variable values do we substitute in to cause that term to disappear. That is, we look at this, what x values do we substitute in to get 0? And of course, that's just 1 and -1. Those are the only two singular points. There are many ordinary points. Here's just a few. You substitute in 2, you get something non-zero here times x prime or times y prime. You substitute in 0, you get something non-zero times y prime, substitute in 5. But really, any number except for x is equal to 1 and -1. So there are many ordinary points, but there are only a few singular points. With the second differential equation, the highest order term, that is, the dependent variable taken to a derivative with higher order of derivative than any other, the only singular point is actually x is equal to 0. There are many other ordinary points, namely any point but x is equal to 0. Here are just a few examples. In the third equation, the highest order term is going to be y to the fourth, and its coefficient is x squared plus 3, and there is no real number that will cause that expression to be 0. So there are no singular points, and therefore some ordinary points, well, pick any real number and that's going to be an ordinary point. Now let's further differentiate, no pun intended, among singular points, and that is to look at regular singular points. Suppose you start with a, in particular, second order differential equation that's linear, and it has a singular point, x sub 0, where again, that x sub 0 is a point such that a2 x sub 0 is equal to 0. If you substitute in x sub 0 into a2 of x, what you get out is 0. We further distinguish this as a regular singular point if the following two limits, this and this, if they both exist and are finite. Remember, you could exist, but not be finite. You could go to infinity with the limit, or it could simply not exist at all. Notice here that we're taking ratios of the coefficient functions. Here it's a1 over a2. Here it's a sub 0 over a2. Both of them are divided by a2. And we know that if we were to substitute in the singular point, x naught, into these, we would get 0. But what we're doing is we're going to see that if we multiply by this, say, x minus x naught, or x minus x naught squared, we want to see if somehow those limits will be finite and exist. So it's a check. We know that we're going to get 0 when we plug in x of naught into a2 of x. But we want to see if these ratios are such that as we take the limits, maybe we get something that's non-zero. If they both exist and are finite, then we would call this a regular singular point. Let's look at an example. Say we have this differential equation. We notice that there's only one singular point. That's x is equal to 0. That's the only value you can substitute in that's a real number, such that this first term will disappear. The question is it a regular singular point? To find that out, we have to compute some limits. We have to compute this limit and this limit, where notice this is x minus 0, where 0 is the singular point, and this too is x minus 0, but x minus 0 squared. Then we take a ratio, first this divided by this, and then second this divided by this. And again, noting that we do square this here. In both cases, we're taking the limit as x goes to x naught, where x naught here is 0. In the first case, we can simplify by taking x times x divided by x squared is simply 1. And in the second case, we right away have x squared divided by x squared. Taking the limit in the first case gives us 1, in the second case gives us 0. In the second case gives us pi. Both of these are limits that exist and they're finite numbers. Neither one are infinity, negative infinity. They both are finite. Both limits exist. Therefore, by the definition, we have a regular singular point. Yay! Once you have a regular singular point, there's a method of finding a series solution, and it goes like this. Let's start with the theorem that there is such a solution. The theorem says that if you have a second order linear differential equation and you've got a regular singular point at, let's say, x is equal to 0, what follows is that there's at least one solution of a series form, and the series form in particular looks like this. We have a series centered about 0, like we've seen before, but the only caveat is now we have an additional plus r here. If we left that off, we would have just the typical type of series solutions that we've been using, but now we have a plus r, where that r doesn't have to be an integer, could be a rational number as well. And if you have a solution of this form, it's called a Frobenius type solution. Let's walk through how we would actually find a particular r value for a solution of this type. This theorem tells us that we can be guaranteed there's a solution, but it doesn't necessarily say how we find it, but we use methods that are similar to what we've already done so far in the case of having ordinary points. So the only real difference here is the fact that we have this plus r, and there's a little more work to do, but largely the idea is the same. Suppose we start with this differential equation here. We notice that there is a singular point at x is equal to 0. We would like to check, is it a regular singular point? That's what we need to be able to use the theorem of Frobenius. That includes checking two different limits. If we do, in one case we get negative 1/2, in the other case we get 1/2. Of course, those are both limits that exist and are finite. That tells us that x is equal to 0 is a regular singular point. Now what we want to do is compute derivatives of our Frobenius type solution. The Frobenius type solution is going to look like this. We compute the first derivative, it looks like this, and the second derivative looks like this. In each of these cases, it's going to get multiplied by some coefficient function. Y will be multiplied by x plus 1, y prime will be multiplied by negative x, and y double prime will be multiplied by 2x squared. In the first case, we end up with this series. The second case, we end up with this, and the third case, we end up with this. Now let's assemble this all together. We'll start by coloring the different terms to help with following what term comes from where. Substituting in the series gives us this very long expression. And now we notice that as far as x to the some power, we have x to the k plus r, x to the k plus r, x to the k plus r. Here we have x to the k plus r plus 1. What we would like is for the exponential expression to always be the same. And since we have x to the k plus r everywhere except for this case, let's go ahead and change the indices here. If we do that, we'll reduce it by 1 here, reduce it by 1 here, and then increase the starting index value by 1. Now, what we notice is that we have a certain expression when k is equal to 0, given to us by these series here. And then after that, all of the series contribute terms because they all have k is equal to 1. This one, and this one all have k is equal to 0. But then after that, they all have k is equal to 1. So we arrange it like this, where the first expression here is contributed to us from these 3 series that start with k is equal to 0. And then after that, we combine the expression from all the different series. So again, the first case is k is equal to 0. And after that, we corral everything together for k is greater than or equal to 1. Now, just like we've done before, we look and we say that this coefficient must be 0. And that's because we have no x to the r's over here. So it must be that this coefficient is 0. Also, as we'll see, it must be that this coefficient is equal to 0. And from there, we'll get a recursive relation that allows us to just compute as many of these coefficients as we would like. But first, let's see what we get from this coefficient here being equal to 0. Now, as we said, the coefficient should be equal to 0 because there's the same number of x to the r's on the left-hand side as the right-hand side. A simplification shows us that we should have this expression equal to 0. And we can factor that to get this. Now, what this tells us is something has to be equal to 0. We have a product of 3 things, 2r minus 1, r minus 1, and c. One of these things must be 0, at least one. It could be more than one. But we can say for sure one of the following is true. We have c not equal to 0, r is equal to 1, which would have this factor be 0, or r is equal to 1/2. Now we want to consider the various cases, in particular when we have the r values being some given number. Let's start by looking at r is equal to 1. But you'd want to also do this for r is equal to 1/2. We'll just do it for r is equal to 1 for the sake of time. Since we're supposing that r is equal to 1, it's true that c naught could be anything. It's not immediately tied to being 0. We could have it be 0, but it could be anything else we like. We could have it be 1. We will end up later choosing c naught to be equal to 1, but we also want to know what the other coefficients are. What is c1? What is c2? c sub 3, and so on and so forth. Let's look at the second expression that we had gotten and generate a recurrence relation from that. That is, we can generate new coefficients from old ones. Our recurrence relation will be this expression is equal to 0. With some algebra, we end up with this, and then this, and finally, we get something like this. Now we reset our work and continue from there. We get this expression, then this, and that's because r is equal to 1. And finally, we end up with this recurrence relation. Now, so far what we have is that r is equal to 1, c naught could be anything, and then the recurrence relation tells us that ck is based on some scalar multiple times ck minus 1. So if you know ck minus 1, you can get ck, and then you can get ck plus 1, and then ck plus 2, and so on. So we define new values from the old ones. The very first one would be c naught, which we said could be anything. Now the simplest non-zero number we could pick would be c naught is equal to 1. From there, using this recurrence relation, we can find c sub 1, because that will come from c naught. That would give us that c1 is equal to negative 1 divided by 3. And then again, we can get c2 from c1. We could get c3 from c2, and so on. We can go as far as we want. But say we know that we can get as many terms as we like. We have that information, we just won't explicitly write it out right here. But how does this relate to finding a Frobenius type solution? Well, we said it should look like this. And if we start writing that out, expand it, we get this. And now we've found c naught, c1, c2, and we could find c3, c4, and so on. We substitute those in, and this is the expression that we get. I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.